Okay, hello everyone, and welcome to the third workshop for early stage researchers under the project EXtremeClimTwin. We are really happy that we can share our experience with you, that somebody will be online and somebody will be on site. We are very happy that we have our lecturers here today with us. And for today's lecture, we have Professor Prof. Wilby talking about climate risk and adaptation indicators and the development of those. So without any further ado, I would like Prof to take the floor and continue. Yeah, thank you.
Okay, all good. Well, good morning, everyone. It's fantastic to be back here in Novi, and welcome to everyone who's joining remotely. Apologies, I can see that I should have worn a plain shirt because that's the first rule of speaking remotely on a video camera, not to have a checkered shirt. So there's a lesson for today. Throughout this program, we've been covering lots of different types of data, from hydrological, from meteorological observations, from climate models. We've been thinking about how to quality assure those data, how to create projections of climate change in the future for rainfall and temperature. Today, we're going to change gear a little bit by thinking more about how this information might be presented and used by decision makers. How do we use climate risk information to inform the public, to help guide decisions about coming climate risks and how we might adapt to climate change? So the broad topic is around climate risk and adaptation indicators, which is essentially about taking climate information, whether observations or from models, and converting it, translating it into different ways of presenting that information to non-expert audiences. And let me begin by just sharing with you one of my favorite ever government reports produced in the UK about 20 years ago was on climate change indicators. I'm going to pass it around. Sorry for those of you beaming in remotely that you can't see this document. But what I like about it is that it takes some very complex information about climate change, climate variables, and it translates it into everyday things. How might this affect crops, plants, animal life, water security? And it contains, as we can see on this opening slide, a wealth of nice imagery and graphs to make this information really accessible. So if I just pass that around, just take a quick browse. I think this is what we're striving for. We're seeking to develop a set of indicators that are sensible, scientifically robust, and communicate key risks to diverse audiences. Moving 20 years on to closer to present, here are some examples of the types of climate change indicators which have been used in the UK by our Committee on Climate Change. And you can see that these have been broken down into different domains. So indicators of risks to the natural environment, to people in the built environment, and to infrastructure. So, for example, if we look at this one here, people in the built environment, percentage and number of new properties built in flood zone 3. So currently in the UK, about 10% of all new homes are still being built in the floodplain, in places that we know will flood. So whether or not we have more extreme floods in the future, which we expect, those homes are going to be at risk. So counting the number of homes in the floodplain is a really powerful example of an indicator showing the exposure of people and property to flooding now and in the future. Some of these other indicators might be a little bit harder to understand. So, for example, the size and spatial configuration or pattern of woodland patches within the landscape. What's that got to do with climate change? Well, green patches, the mosaic of habitats is a useful indicator of biodiversity and how plants and habitats might be impacted by climate change and other factors in the landscape. You can see that there's lots of different types of indicator here, some aimed at water companies, some at planners and developers, others to do with water management and protection of fragile habitats. What we're going to be doing this morning is looking at this topic in 3 steps. So step 1, we're going to use some examples to think about what's the purpose of a climate risk indicator and what is the ideal, the perfect attributes of a climate risk indicator. And I'll be setting a few tasks to help us move towards understanding that. Secondly, we'll be looking at the development of a climate risk indicator, drawing upon some of my research in water temperature as an indicator of risks to river ecosystems. And then thirdly, in step 3, we'll be thinking about devising some climate risk and adaptation indicators for Serbia as a first step. Is that all clear? Okay. Right then, so let's begin with this map, which is an example of emergent climate risks. In this case, we're looking at the spatial pattern of dengue fever, so a mosquito-borne disease, and it's spread in space and time across China. So if we look in the top left-hand corner, we can see the distribution of dengue in the present climate under a low emissions scenario, and we might contrast that with the end of century pattern for dengue by 2100 under a very high emissions scenario. So the question is, you know, these sorts of maps appear in the scientific literature. They reveal the changing extent of a climate-related risk, but what would we do with this information? So turning it around, I'm aware that, well, I think I know that there's cases of dengue here in Serbia from about 2009. Well, certainly the mosquitoes that carry dengue are already present in Serbia. So this is not an abstract idea about this is a risk only to China. It's a risk for Serbia too. So what would we do with this information? That's a question to you and anyone online who might like to put an answer into the chat. Any thoughts? What can we do with this information? Yeah.
I think we should spread it on social media because that's the way that information spreads the best.
Yeah, excellent. So using these maps to raise awareness, to educate people of the risk, to be aware of the risks posed by these types of mosquito to your health, to your children when they're out in the garden at certain times of the day or in parks or countryside. Anything else?
We could hope that it will reach certain people who make decisions and hope that they will not ignore the information.
That's right. You'd think that maps like this, that government and health authorities might improve the surveillance systems for tracking the emergence, I think the word's the epidemiology of this health threat in the population. There's probably another thing that we could do with this information as well. Spatial information. Yeah, Tim.
Well, we can pinpoint the risk locations, the high risk locations that are of utmost priority for possible mitigating measures, etc.
Exactly. So we can identify the hotspots of risk in China. In the case of China, it's in the southeast. So you might concentrate, let's say, the application of insecticides or management of stagnant water bodies, or you really concentrate the mitigation measures in those areas of highest risk. So you can see that just from this very early example, a climate risk indicator is a really, really powerful tool that can inform lots of useful actions now, and we can get on with this now. We don't have to wait till 2100 to apply this information. Whoops, let's do that. Stick with that. So we can think of climate risk indicators as undertaking 3 sets of tasks. So they can help us understand the nature of the hazard, who's vulnerable, who's exposed to the climate risks. We can use climate risk indicators to track the impacts of climate change on all sorts of different aspects of society and the natural world. We can also use climate risk indicators to measure how much effort we're putting into adapting to climate change, and then over the longer term, how effective those measures have been in addressing the identified climate risks. So here's again some examples from the UK. An example of a climate risk indicator used to measure exposure is the percentage of properties in administrative areas that are exposed to high, medium, low, and very low flood risks from rivers and the sea. And just for interest, I've located on the map where Loughborough sits, and you can see if you glance across to the red map, Loughborough or the Charnwood area actually has quite a high level of exposure to flood risk from rivers. So this map, again, as we were saying earlier, can identify those hot spots of risk. Where in the country do we have highest exposure of people's homes to flood risk as a starting point to think about what we should be doing to manage that flood risk? For example, might a map like this be used to concentrate investments in new flood defences, or raising, applying more strict standards to developments and proposals for new housing in these areas? Here's another one, but now we're looking at potentially the impact of climate change on wildfires, and the indicator here is the number of hectares of land that has been destroyed by a wildfire and how that's changed through time. So you can see there's a lot of variation from one year to the next. You can see that the data set is rather short, so we're not yet in a position to say whether there's any long-term trend. And there's also some other issues with a variable, an indicator like this. What might be problematic about reporting the burnt area as a climate risk indicator? Any thoughts?
Because maybe some burned areas are not caused by climate change, other people.
Absolutely, there's a huge human factor in this, isn't there? So the climate, whether it's hot and dry, sets up the conditions for a wildfire, which might be started by a lightning strike, or more likely, for some of the big fires we've had recently, someone leaving a barbecue on a piece of grass, or dropping a cigarette or something like that. There's a human element to the initiation of these wildfires, so it makes it a more complicated indicator to interpret, because there's the natural and the human factors at play. Okay. Yes, please do.
This year in Montenegro, there were a lot of fires on the coast. on the seacoast.
Yes.
So people were scared how that can appear and spread so much. But actually, what was going here is that the people, investors who want to build hotels, they put fire by themselves, and then some protected areas burn, and then they are not protected anymore. There's nothing to protect because everything is burned. So they are able to invest in some hotels.
Yeah, thanks for sharing that. That's a very sad example, isn't it, of the human element in wildfires, and quite an extreme one. But I'm sure that's something that probably happens in other places as well. But it's a really great example of how it's more than just a climate change indicator. So we have to be careful how we interpret these types of data. So thanks for that.
Because only these fires occurred in really pretty places.
Yeah, thanks for sharing that. Yeah, Tim.
I just want to add, this is the reason why forest fire analysis in Serbia are closely related to the data provided by the Sector for Emergency Situation within the Ministry of Law, etc. So these two data sets are very, very good to combine when performing these kind of analysis.
Yeah, thank you.
To perform the analysis of forest fires as a physical phenomenon and total number of forest fires by different accidents or other factors.
Thanks for raising that point, because we'll come back to that later. That to maximize the value of some of these indicators, we do need to bring together different types of data, the human and the natural factors, to really understand what's happening. Here's another type of climate risk indicator, but here it's being used to measure the extent of adaptation. So in the UK, there's quite a strong push to implement the so-called nature-based or natural flood management systems. So these might be wetlands or sustainable urban drainage systems, things like that. So working with nature to manage flood risk. And so simply counting the number of schemes that have a nature-based element to them gives us some baseline information about the extent to which local flood risk is being managed in these ways. Okay, so the data like this can provide us with a baseline to see whether there's more or less action in this kind of area in the future as a way of reducing flood risk. And I emphasize reducing, not solving or completely eliminating flood risk, which these methods won't do. And then another example is from the water industry, where here what we're looking at is the amount of investment in millions of pounds made by water companies in what we call resilience measures. So for a water company in the UK to be more resilient to drought and climate change, one option is to increase the number of connections or pipes, let's say, between sources of supply and points of demand. So we can move water around in the event that one source fails or is taken out by drought or a water quality issue. Water can still be brought into the demand center from elsewhere. So the number of linkages in the water distribution network and the amount of investment in that kind of infrastructure can be regarded as a measure of improved resilience to drought and other impacts on the water supply system. Is that clear? Okay, so just using that, then you can see the extent to which water companies over the last decade have been increasing a lot of investment in these improved connectivity of the water supply, the water distribution system, as one action to enhance resilience. And this is perhaps one of my favorite ones. It shows the growth in the UK wine industry, which is certainly probably one of the few positive stories of climate change in the UK. The warmer temperatures, the changes in the climate have really enabled the growth of our wine industry. And when colleagues and friends came to visit us in the UK, I took them to one of the earliest vineyards in the UK, which was actually established in the 1980s. So that was set up a long time before concerns about climate change became so mainstream. But you can see just how much area has increased. But we might have situations in other parts of Europe where the curve might be going the other way, where conditions are maybe too hot or even too dry to sustain certain types of wine production. And there are parts of Europe where viticulture is certainly under stress. It's not a positive story like it is in the UK. So what I'd like you to do now is to spend just 5 minutes. If you've got the slides in front of you, you should be able to click on the blue hyperlink there to scan this report. You should be able to download the report, or you can obtain the report from the shared folder. And what I'd like you to do is to just look at this report, which is a summary of some of the research undertaken into the development of climate risk indicators in the UK. And I just want you to look at the first 5 or 6 pages, just quickly scan that report and see if you can identify some of the hallmarks or some of the features of an ideal climate risk indicator. Okay, does that make sense? So look at the indicators, look at the short narrative, and just jot down what you think might be useful attributes, useful features of a climate risk indicator. So I'll give you just 5 minutes to browse that. And if anyone online, if you've got a question again, please just put that into the chat and we'll try to answer that. Is that all clear? Okay. Has everyone been able to download the report and access it? Yeah? No? Does the link not work?
It works.
It works.
Yeah, it works.
Let's see. Go to the
There's a link in there.
PowerPoint.
Yeah.
One that's on the slides.
Yeah, it will work when it's in there's presentation mode.
Yeah.
So you can easily download it. Also, there is the same report in the shared folder.
Yeah.
In the PDF. Yeah.
Okay.
There are 70 indicators.
70.
Yeah.
We see we're super optimistic. We can find data for 70 indicators.
Yeah.
These general ideas, just the ability to see the narrative. Just and first, just the first page and a half. Just you're able to look at that, see, pull out any general ideas. How do we get the chat up? I just click on this one.
I can. As he's saying hello, can you please share the link to the chat, please? Yes, you can share.
Yeah, thank you for that. Yeah.
Yes.
Just 2 or more minutes, and then we'll just share some ideas from what you've looked at. And for those of you just obtain the link, you know, hopefully you'll recognize some of the points that we will draw out. Okay. Few more in the chat.
Those things text me and I share the link. Yes.
Bonjour, Anne-Sophie.
Yeah.
Bonjour Rob.
Okay, let's see what we can find from this. I'll put you under pressure there, some of you who have only just obtained the link, but I hope as we go through these ideal attributes, they will make sense to you. So anyone, let's start, anyone online, if you'd like to suggest, what would be something good to have in terms of a feature of a climate risk indicator? Anyone like to put that into the chat? I think we've got one there.
That's me. I'm writing it in writing chat, just unmute
Okay.
and speak.
Yeah. Any thoughts? Okay.
Here, life. For life. So I ideally would like to have something that is updated regularly. So if we are building our features, I would like to have some features that were updated. But does that, for example, it could be number of holidays per year, for example. But if you would like to fine tune our risk, Then I will add additionally this second feature we will be input, but taking with precaution because, for example, if you are taking information about numbers by days per year, I would like to have also number of number per area of the green roofs installed in our urban areas.
Okay, excellent. That's a really good example for the first one, perhaps on our list. And for those of you remotely who might not have heard that completely, the suggestion is we needed records that are readily updated. Okay, so we keep them up to date, and we're able to track the emerging risks through time. We don't, the data collection doesn't come to an end. Okay, that's really, it's a really important one, as we'll see later on. Anything else?
Number of households in the affected flood risk areas leakage. That's from my office. Number of households in the affected risk.
Okay, perhaps. So we've got the, it's readily updated. Here are my 10 suggestions. Okay, well, these will all become clearer, I hope. So readily updated, we see as it comes in at number 7 on my list. Some of these are really obvious when I spell them out like this. So we want to be able to benchmark the present risk. What is the present conditions like? We want an indicator that is sensitive to climate change. So you've got to have something that is going to manifest the climate change signal. It's going to correlate with something to do with climate change. It's got to be a metric that makes sense to a decision maker or a public audience. Ideally, we want a really long record. So remember, look, I was saying the wildfire record's just too short in the UK to say whether there's emergent trends. We want the long record. We want the data to be publicly available and accessible. We want high quality data. As we've said, we want it to be readily updated. Cheap or low cost to keep going into the future. And again, as we were talking about, in the case of the wildfire, no confounding factor. So ideally, the human influence on the indicator would either be very small or understood or described by other data, as in the case of wildfire. And then finally, we want indicators that will reach out to non-expert audiences, not only decision makers, but to the public. So I think that, I hope you can see that they're kind of quite common sense things that we would want to see in an indicator. But as we shall see later on, it's often very hard to achieve all of these in any given indicator. Okay.
Hello.
Now then, let's just look at these indicators here, which show different trends through time. So what we've got on the horizontal axis is the change in global mean temperature. And then we've got a response of some imagined indicator. So it might be a linear relationship, bounded, accelerating, delayed onset, or with this sort of curve shape. So again, I'm going to give you perhaps 2 minutes to just look at these slides and think, what might be the indicator? What might be the variable on the vertical axis going on there? So what variable might change linearly? What risk indicator might change linearly? What might go in an accelerating or exponential form, or in this U shape, for example? Does that make sense? Okay, just so again, just think about that for a minute or two. Yeah, if you can keep an eye on the chat.
Yeah,
Yeah, thank you. Yeah. All right. Anyone going to be brave enough to label any one of these? This is I put this in front of my students at home, my master's students. It's a pretty tough question to solve. Sorry?
We are enthusiastic here, but we work with adaptation. They want to speak first.
Yeah.
So linear, with the increase in global mean temperature, we will have an increased number of hot days per year.
Yeah, that would be good. Yeah. So.
And with the delayed onset, maybe something with the algae bloom, because the temperature of the water is not changing linearly with the change of the global mean temperature, for example.
Okay, so Diana's suggesting that for the linear one, that could be the number of hot days per year, let's say in Novi Sad, or even globally as a very strong association between the two. Delayed onset.
Something to do with the warming of the waters and algae blooms.
Yeah, so perhaps you have to have a certain amount of warming before the algal growth or the water quality problem really takes off. So it's an example of a threshold or a tipping point in the data. Okay, anyone else?
We have a data for linear, the same as Ghana.
Yeah.
But, for accelerating, perhaps if we're looking at these indicators, we can say that the accelerating number is for number of people with radical respiratory conditions.
So this could be some sort of health-related indicator. Heat risk, respiratory risk, maybe. Yeah.
And multiple drivers, perhaps the indicators of area of agricultural land covered by crops at high risk or low risk of soil erosion, because it's not just one factor.
Okay, that's an interesting one. Yeah, yeah. So that you might see that as a soil erosion indicator, where there's a point where the combination of climate changes produces the soil risk because there's perhaps a response in the vegetation cover, but then with further warming and drying, then the risk increases. Very good. Okay. Any other thoughts? Do we have any ideas online? Okay.
This boundary is very difficult for me.
Yeah.
When it reaches certain increase in temperature, it goes steady.
Yeah.
So.
Would you like to know the answer?
Yeah, please.
Okay. So you've given me some great answers, ideas that work just as well, but these are the ones that I might have thought. So air, water temperature, or heat waves we had. In place of soil erosion, I had rail disruption. So lower amounts of warming, there's still a little bit of snow, so the rail system gets disrupted by snowstorms. A little bit of warming, the snow goes away, so there's less disruption. And then with much more warming, you get buckling of rails and energy blackouts and things. So there's an impact there. Sea level rise is your classic accelerating risk. Yeah, I think we recognize that there's a species tipping point here. but this one might be the heat health bound, that once 100% of the population are, let's say, exposed to dengue, then you can't have more than 100%, and I'm emphasizing the word exposed. So let's say temperature increases, the range of the mosquito covers the whole of Serbia, or the whole of Europe even, Southern Europe. So beyond that, you can't have more than 100% of the population exposed to the dengue risk. So we can see that the risk indicators can take many different forms. They can give us an insight into tipping points and thresholds and different kinds of vulnerability. Does that make sense?
Yeah, I was thinking about this bounded. Maybe
the bounded one.
Maybe like the colors of the corals, because one day they will all bleach.
Yeah.
Yes,
that's a great kind of example. So that might be the fraction of corals bleached globally, or in a particular part of the tropical oceans. It could be amount proportion bleach. So beyond a certain marine temperature, all the corals are bleached. Yeah. Okay. Very good. So I'd like to now sort of bring this a little bit closer to home. So what we've been looking at are national indicators, but we can use climate risk and adaptation indicators at all sorts of different scales, even at the scale of a university or a town, as we're going to look at it. So take Loughborough University, my own university, is a huge campus, but it's exposed to flash flooding and flooding by local rivers, which we can see. This is our flood map, and the blue areas indicate the small streams and rivers that flood quite regularly and impact not only the campus, but also the neighbouring town. In fact, actually, I used to give lectures to second-year students in a building that actually sits in the floodplain, lectures on flood risk management. So that was always a bit ironic. So it's a campus that's vulnerable to flood risk. So having an indicator of how that flood risk is changing through time can help the facilities and the management teams to understand how the risk and the impacts of that might be changing through time. So there's physical damage to property, people's cars, flooding of infrastructure. We lose power and IT services, and there's interruptions to access to campus as well. So sometimes you can't get onto campus because the entrances are flooded. And we understand the conditions under which these floods occur. Essentially, if we have about 25 millimeters of rainfall in a short period, that's enough to cause the local rivers to flood. We've got models that can help us to stimulate the development of the flooding on campus, just to understand which buildings and facilities are most at risk on campus. And here's one of the roads that leads to the one of the entrances to the university. So this was the situation on the 1st of October 2019 when I was coming to work. I had to drive through this, and being a good climate scientist, found a dry spot to park my car, and then went back, got my shoes very wet to take the photographs and just to record the impact of this local flooding event, which basically cut off access to the university for about an hour. And we again, using local data that we collected on campus from our own weather station, relating it to local river levels, we can see a very clear association between the heavy rainfall and the rise in the local water level. And basically we know that when the water level in the river gets above about 0.5 metre, this is going to be the situation. So we know the amount of rainfall that's problematic. We know the local river level that's problematic. So there we've got the basis of a simple indicator. We can count the number of times each year we get 25 millimetres, or we can count the number of times each year the water level is above 0.5 metre. And that gives us a very simple indicator of changing flood risk on and around the campus. And that's exactly what we've done. We've started to use our own rainfall data, information about water levels, to track the occurrence of 25 millimetre events, which is this one shown in yellow, so just a handful of events each year on average, and there's not enough data yet to show a trend or anything like that, or the frequency of these events above 0.5 metre. So you can see a lot of variation from one year to the next. But even from these data, we can see that the university is exposed to at least one disruptive flood event per year, and that actually has an impact on staff access, information systems, damaging electricity supplies, and so forth. But these simple indicators can be used to track that risk through time to see whether it's going up or down, whether there's an increased frequency. We can also start to think about use this information to start to think about some simple measures that can be taken on campus, protecting green spaces, perhaps increasing some of the flood embankments in and around the campus, protect critical infrastructure, improving the design of new buildings, deterring further development in those areas of campus where we know there's flood risk. This is the important point, that we're connecting the climate risk information. We're using it as a way to take to managers this message that this is a potentially costly thing to the university, and we need to be taking some practical steps to manage these risks, because the climate models suggest that this risk is going to grow in the future. And sometimes it can be just really unglamorous solutions, like ensuring that local blockages are removed, so that you keep the silt and the woody debris out of the drainage network to stop it backing up and causing local flooding. Very simple management things that can reduce a lot of damage to the local infrastructure. We're also thinking about not just flood risk, we're thinking about how biodiversity might be impacted on the campus. We have a very large campus with lots of mammals, birds and insects and plants. And we're just beginning to assemble audits, lists of all the animals and species on campus, create that baseline data set to understand how it might change through time. So bluebell woods are a key feature of ancient woodlands in the UK, but they're under threat from a variety of factors. So even measuring the date of the first flowering or of the blossoms can tell you what's going on with that ecosystem. Recording the number of invertebrates in the many ponds and waterways on the campus is an indicator too. So we're looking at recording the type, extent and condition of habitats. We're looking at key habitats like wetlands and ponds to see how the species mix is changing. And we're recording the first flowering of phenology, as we call it, of the species. How is that changing through time with the changing weather conditions? So I hope that makes sense. Now a chance for you to perhaps just reflect on what simple indicators might we have to measure any climate risks to staff and students and infrastructure on the campus at Novi or of the city as a whole. Flood risk might be one of them. So let's just spend a couple of minutes just again, maybe thinking amongst yourself, discussing what type of indicator might you propose for the University of Novi Sad or the city of Novi Sad, or for those that are joining us remotely, think of that for your own university or your own home city. What would be the indicators that you could measure relatively easily to track climate risk through time? Does that make sense? I'll give you 3 minutes to think about that, till 5 past the hour. And again, those of you that are joining us remotely, please just type in your suggestions into the chat and Diana will share them with the group. Okay? Okay, so do we have any thoughts and suggestions? What indicators might we develop for our own universities or host city? Any ideas?
Okay, I know that some biology students from our faculty are counting birds and their species and how many of them they find. They're doing it a few times per month, and this is going on for only like 5 years or so. So they have some huge database already for bird migration in Novi Sad, and I think this is going to be some of these PhD thesis one day.
Yeah, excellent. So, I mean, there's lots of really positive things from that. It's an existing data set. So you've got a good start with 5 years. You can engage students in the collection of the information as part of their studies, and over time you can build up a nice indicator of just the number of bird species as a simple indicator. But of course, the number of species is affected by a host of other factors beyond climate change. So it would be a very interesting indicator to track through time and to also reflect on, in addition to climate, what are the other factors in and around Novi Sad that are affecting the species richness of bird life. That's a great example. And then, I mean, if someone took charge of these data centrally and organized them, so each year, whether it's bird counts or other data that students are collecting, this could be a very powerful resource for the university or the city as a whole. That's a great suggestion. Anything else?
We haven't checked my potential soil moisture deficit.
Soil moisture deficit, yeah. Where might we record that, do you think? Are there sites on campus or in and around the city?
Probably around the city.
Yeah, as an indicator of stress on the agriculture, which we can.
Yes, and also the green areas, stress of the green areas in the city.
Yeah. So I wonder if greenness is an indicator, we can gather greenness information from remotely sensed data, the NDVI. Might be used as an indicator of drought in and around the city.
Yeah.
Okay. Anything else?
Maybe we can use consecutive precipitation days in order to better understand urban flooding in certain city areas.
Yeah.
Novi Sad, for example, this is a big problem already.
Yeah. So having, just like on the Loughborough University campus, counting the number of days with rainfall above a threshold. Now, I could put you really on the spot now and say, does anyone know what the threshold is for localized flooding in Novi Sad? So how much rain has to occur before there's localized flooding? So in the case of Loughborough, we know 25 millimeters within a day, often falling in a short period, is enough to cause localized flooding. If that threshold is not yet fully known or understood for Novi Sad or the site here, that could be an interesting little project for a student to look at the data, match the rainfall data to the local flooding, and identify what that threshold is, and then count the number of days each year where you have rainfall above that threshold. It can give you that indicator of flood risk.
But also the change in land cover, because here we have an interesting situation in our side regarding the urban.
Yeah. That's construction, yeah.
That you would have some touchy stuff regarding the should it be the populated area in the Danube Valley or not? So I think this is something that also needs to be addressed.
Yeah, exactly. Life is never as simple as I've suggested, where you can just measure the rainfall and infer the flood risk, because cities grow, land cover types change, drainage systems age and decay, or are built to different standards. So it's never as simple as I've suggested. So, you know, having that information on the urban extent and type of urban development helps to interpret the information. It also responds to that point in our shopping list of 10. You have these confounding factors, these other factors that make the interpretation of the climate signal perhaps a little harder than it could be. Okay, any other thoughts?
There are two suggestions in the chat.
Thank you.
Air quality warnings, number of not working days caused by extreme weather, and of course changes in the weather data near the meteorological station.
Yeah, all excellent suggestions. You know, again, forgive my ignorance, I don't know whether the University of Novi Sad has its own weather station, but if it doesn't, an automatic weather station or something can be a very powerful teaching tool, as well as a way of gathering these data sets needed to develop a long-term risk indicator. Okay.
There is another comment, changing in flood magnitude.
Yeah. So having information about the flood peaks in and around these cities or on the campuses that we're looking at, using that local information, tracking the peaks over threshold through time. It's very useful. The air quality one, that's a good one, because poor air quality is often associated with heat waves,
lack of green space,
and these other things. So an air quality indicator, as I understand it, particularly here in Serbia, would be an interesting one to have. Yeah. Okay. Excellent. All very good suggestions. Shall we take a little break now?
Yes.
And let's return at 20 past the hour for part 2. Is that okay?
I think we can have a break 15 minutes.
Oh, okay. Well, let's.
11:30, and then we.
Okay. Well, okay, everyone who's beaming in, we will return at 1/2 the hour, whichever time zone you're joining us from. Okay. See you in a bit. Okay. Right. Welcome back, everyone. Hope you had a nice break there. We had a really great question in the chat about the.
I can read it again.
Okay.
I have one question regarding one of the first slides. Is there a reason for the big jump in the burned areas between 2011 and 12 and post-period 2017? Some adaptation action needed.
Yeah, thank you for that question about the sudden jump in the burnt area in the short record from the UK. So I think we have to be very careful in interpreting changes from one year to another in a short record like our burned area series for the UK. That's because just one very large wildfire can cause extensive damage over a large area. So it might be a single event that really got out of control. We've had some examples of that in the UK recently, where large areas of moorland have been burnt by a single event. So I think that the short answer is that we need to take a much longer term view in terms of the burnt area before we can say whether there's any long-term trend in the data and whether or not any actions have actually had an effect on the indicator. So I hope that answers the question. Okay, short answer is just several years of data are probably too short to make any inference about the effect of management interventions. Okay, so let's continue with part 2, where I'm going to walk you through what it actually takes to develop a climate risk indicator in practice. And in previous sessions through EXtremeClimTwin, I've been talking about water temperature. It's one of my pet research subjects, and I know there are others in the room who are also interested in water temperature. Water temperature is a really important variable because it not only reflects changes in the climate, the river flows, the temperature, the bankside vegetation, but it's crucially important to the water chemistry and also to all of the plant and animal life in the river. So it's a really powerful indicator of changes in the freshwater environment. Oops. Thank you. Now in the UK, efforts about 15 years ago led to the creation of a national water temperature archives. So we've got a lot of data to work with, and these water temperature data were not originally collected with climate research in mind. They were collected as part of routine monitoring and compliance of water quality in rivers and lakes and the coastal zone around the UK. But there may be such data here in Serbia and in the countries joining remotely that could be used as a basis for developing a national water temperature indicator. Why do we care? Well, there's the ecological and the water quality dimension, but also to highlight the fact that rivers are warming all over the planet, including here in Serbia, where some researchers, named Mazarin, analysed the data and found that the Danube, for example, is warming by about 0.5 degree per decade. So to emphasise that this is a phenomenon that's occurring most places on Earth. And in the UK, this gives you a sense of the amount of sampling points we've got. And in this particular study, it was shown that nearly 90% of the sites were showing a warming trend in the UK. The response to this warming has been around what can we do to keep rivers cool? And those responses might be typically around the development of shading through planting of trees on the riverbanks. For small rivers, that's obviously going to be one option. Planting trees along the sides of the Danube is probably going to be less effective at causing any benefit, but planting trees along the banks of the headwaters of the Danube might have a benefit. It's a very simple idea: plant more trees, keep the river cool, and offset some of the climate change that we anticipate. It's a very attractive idea that's gained a lot of momentum in the UK, and there's been development of guidance for landowners about tree planting. But the scientific evidence base around the amount and type of tree planting is still very much in its infancy. So some really basic practical questions about where to plant the trees, what species might we select, how much of the riverbank needs to be planted to achieve a given benefit, what are the other ecological side effects of planting those trees, what are the impacts on groundwater and flooding. So even a simple idea like plant trees to increase shade to keep rivers cool opens a large number of quite difficult scientific questions to address. And the realization of that led me and some other colleagues to set up some very high density water and air temperature monitoring experiments in the central part of England. And I've referred to this data set, I think, in previous workshops, which provides very high resolution in space and time water and air temperature data to try and understand what are the local physical controls affecting the water temperature, not just the plants on the riverbank, but the hydrology, the presence of springs and other natural features. How do they control local water temperatures? So going back to our 10 ideal attributes of a climate risk indicator, benchmark, sensitive to climate, etc., etc. What I'm going to do now is to say, okay, with all the data we have in the UK, can we build a climate risk indicator that addresses all of these points? how well can we do? What do we score out of 10 for our water temperature indicator nationally? So I'm going to illustrate each of those as quickly as I can. Then I'm going to set you a little task at the end. So yes, we can benchmark the data because it's high resolution space. We've got a great amount of spatial information. So if we look at, this is a chart going downstream, changes in mean maximum water temperature. So this is in the headwaters and this is in further downstream. You can see basically the river's getting warmer the further we go downstream. And here I've indicated one of those thresholds. In this case, 20 degrees Celsius is a potentially harmful threshold for the fish species in this river. So straight away, we're able to identify those parts of the river that are potentially hazardous to the aquatic life. We've identified what we might call the hot spots in this river. We can benchmark straight away. Just to give you a sense of where the cool spots are, there are all these natural springs along this particular river where there's cool water feeding in from groundwater. It locally reduces the water temperature. So that's another sort of background factor that we need to take into account. And we can start to identify the locations of the really hot water. This is one of the hot spots. And if you look at this image of the landscape, you might imagine why this is trapping the heat in this steep valley with relatively little shade. The water's exposed to a lot of solar energy, both at this site and from upstream. So benchmarking is good. Is water temperature sensitive to climate? That's the second attribute we're hoping for. Yes, and it's sensitive at lots of different timescales. So if this is the water temperature index in the upper parts of the river, we can see that the water temperature is responding to lots of different climate indicators. So in this case, when we have heavy rainfall in summertime, we often see these spikes of higher water temperatures. So you might be thinking, well, how on earth can the maximum temperature in this river be recorded at midnight or at 2 o'clock in the morning when there's no sun? It's because the heavy rainfall is causing warmer waters from soils and riparian areas to be pushed into the river, causing this spike in water temperature. So sometimes the connection to climate is not obvious. Here we're revealing a connection between heavy rainfall and maximum temperatures in this part of the river. And indeed, if we look through time and each of these curves is for a different location, what we see is the movement of that thermal spike as it drifts downstream. We term this a thermal shock wave, just to attract attention from readers. There's a heavy rainfall in the headwaters cause the initial rise in temperature here in the black and the red right at the top of the river, and then through time we can see that thermal shock wave moving downstream, and often in this case, for example, in the lower reaches, causing the maximum temperature to arrive well after dark, which is, you know, a very surprising thing. And obviously that's going to have an impact on the fish and the insects and everything else in the river. With climate change, we might expect more frequent summer downpours and more frequent thermal shock waves. And so that raises the question, what impact might this have on the freshwater ecosystem? And this is more conventional stuff where we can simply relate the water temperature to air temperature in different locations. This is for 4 different sites: a headwater site, a hot spot, a cool spot, and somewhere in the middle of the river. And most research tends to show this logistic relationship where you've got the air temperature on the lower axis, water temperature on this axis, and it shows, oops, this S-shaped curve where we have very rapid warming association in the middle here, and then a flattening off. At higher temperatures, you've got more evaporation, evaporative cooling, and so the response is non-linear. So we can relate to temperature. And over decadal timescales, here we're showing that really dense distribution of water temperature sites across England over about a 20-year period, and showing how that pattern changes depending upon the North Atlantic Oscillation Index. So it's basically a measure of how stormy or wet the summer might be. So if you squint and you look at the screen, you can see somewhere years where there's lots of red. But during this particular period, the majority of years tend to have blue spots. They were cooler because of the negative index. So there's the year-to-year variability here in the atmospheric circulation patterns that are affecting the rainfall, the temperature, the amount of river flow, and the water temperature on the ground. So I hope through those examples, you can see whether it's at the event scale of an individual storm, through a season, through year-to-year variability, there is a strong connection between climate variables and water temperature. So that's a good big tick for that second metric, that second criteria. How relevant is it? Well, water temperature, as I've already indicated, has a really strong influence on freshwater ecology. For instance, during warm years with warmer temperatures, the mayfly may only take 1 season to mature, hatch, and then fly off. In cooler years, it takes 2 years for eggs to turn to larvae, to emerge, and then to fly out. So the water temperature can actually determine whether a mayfly takes 1 or 2 years to reach maturity. And that has all sorts of knock-on impacts for the ecosystem, the birds that feed on the mayfly, the fish that feed on the mayfly. So it has relevance. It has relevance as well because we can start to look at the effect of bankside vegetation on the energy balance of the river. So this is a rather complicated graph to understand, but basically what we've got here is distance from the source of the river downstream. The black line shows the energy, annual radiative energy received in that part of the river without any vegetation. So this is all done in modeling in a modeled environment with a digital terrain model to simulate the energy received. And then the green line signifies what that energy balance is with trees planted alongside. So the black, you can see, drops down here. So there's lower energy in this part of the river because of steep ravines and shading of the river by the landscape. Then if we plant rather optimistically, 30-meter trees, or imagine a 30-meter tree, how much that reduces the energy balance. Now, at the time, when we did this analysis, no one actually questioned the 30-meter tree assumption. With hindsight, I've often asked myself, how long would it take us to get to 30 meters of growth as an adaptation? Could be a century, so we might have used a smaller number like 5 or 10 meters in this type of study. But you get the general idea. It helps to show the sensitivity of the water temperature to the action we're taking, which is tree side planting. So it's relevant, it passes that third test. This is just more of the same, it's relevant, we can use more analysis to say how much tree shade do we need to plant to cool the river by a certain amount. And basically the answer is that to reduce the temperature by one degree, we essentially need about 1 or 2 kilometers of tree planting. And that's a very useful rule of thumb that you could give to a landowner and say, if you plant this amount of trees, this is the benefit you're likely to get. So again, it's relevant information. Fourth criteria is, have we got enough data to look at this in the long term? The answer is yes. At some sites in the UK, we've got water temperature data going back to the 1970s. So we can look at how this indicator has changed over a 50-year period. And here, for a particular example, one of my favorite rivers as a child, I used to go down stepping stones and in the water, the River Mole in southern England. 50 years of data showing a lot of year-to-year variability. Are there any trends in these data? Hard to discern by eye. Are the data open? Yes, they are. The Environment Agency puts our water temperature data into the public domain, so it's possible to access any of this information. But the sheer volume of the data and the variable quality of the information means we can't just go in and take the data and use it uncritically. And that may apply to your own national data sets. If you access them, we've got to sort of apply some criteria. So when we were thinking about this national water temperature indicator, we applied these sensible steps to help quality assure and select the very best sites we could find. So we started off with, in 2018, the data sets there were nearly 1,200 sites we could pick from. So that's our beginning set of rivers. And then we were looking to remove those sites which have well-known impacts of year-to-year variability. We wanted to capture the sites where there's a much smoother long-term trend, and that reduced it down to just under 200. Then we said we want to have at least 200 measurements, a big enough data set to say something sensible. That left us with just 30 sites. Then if we said, if we want our site to be within 5 kilometers of a river gauging station, so we can relate the water temperature to the river flow down to 10, then if we look at the remaining sites and say, how many of these have been affected by artificial influences like upstream reservoirs, water abstractions, or effluent return, we're down to 6. Once we filtered those out, we're just left with these 3 sites where all of those quality criteria are met. But I hope you can see from that step by step, you can filter out the sites that would be difficult to interpret or don't have enough data or poor quality in developing this index. Do we have a reliable set of measurements? It depends. There's a lot of literature that tells us we have to be really careful about how and when and where we measure water temperature. So this graph shown in red shows the effect of a water temperature probe that's been exposed to sunshine. So if it's in the river, but it's not properly shaded, you can get these artificial spikes in the warming, so that can corrupt the quality of the data. So you've got to be careful how you install the equipment protect it from obvious things like direct sunlight. And I think I've shown you this graph before, some of you before, on the data quality session. It's one of my favorite graphs because it shows how an apparent trend in the data can be absolutely nothing to do with climate change, but caused by something else. So what we've got here is the date, and this is the time of day at which the water temperature sample was taken by the field officer. So the story is that in the 1990s, the field officer would go and take the water temperature at 9 o'clock in the morning, just after breakfast. And then by the mid-2000s, taking that same water temperature sample at lunchtime. So just through time, this is a very powerful quality assurance check, is to plot the time of measurement and how that has varied through time. Just that drift towards later sampling of the water temperature has introduced an artificial warming trend into that record, because a measurement taken at this time of day is bound to be on average warmer than a measurement taken at this time. So that's an example of how a very subtle shift in measurement practices can produce an artificial trend in a climate risk indicator. So you can see I've highlighted this header in red to denote that I think it fails our tests. We have to be careful about the reliability in this case. Readily updated. Are the data still being collected? And this is a bit of a sad slide because it shows the shrinkage of the amount of data collection through time. So 2001, you can see how many sites we were measuring water temperature in England. And then nearly 20 years later, how the number of sites has shrunk. And that's largely driven by cost savings. So it's costly to send people to collect the data. So there's constant pressure on government agencies in the UK and elsewhere to rationalise monitoring programs, and that can introduce shrinkage of the network. It can mean closure of even very long data sets may be closed. So readily updated is often one of the key things that we struggle with. We might have an excellent water temperature record, but then if the decision is taken to stop collecting, then that's a really big impact on our indicator. So that harks back to my opening statement. Fun and frustration. It's frustration in developing these types of indicators when decisions about networks are taken which are outside of our control as researchers. Affordable to maintain. It doesn't cost much to gather these data and keep them going, but there is a cost. Someone's got to pay for it. The government agency has to find the money. And of the 6 sites that we identified for the national indicator, we've done this work just before the pandemic began. And then obviously many monitoring systems around the world were impacted by the pandemic. 3 of the sites, we're not sure whether or not these optimal sites are still being continued, perhaps as a legacy of the pandemic or attempts to manage the costs of monitoring. Number 9. We want to be careful that there aren't artificial influences on the data set. And this is a really subtle thing that's been happening, not just in the UK, but all across Europe. And there's this wonderful site on dam removal across Europe, for those of you who are interested. When you click on the hyperlink of the slide, it takes you to the data set that's showing how many structures and weirs and other things are being removed all across Europe to improve the passage of fish, to return rivers to a more natural state. And so in the rivers in the UK, many of them have had these low-level weirs that create little ponds, and they might have been built 200 or 300 years ago, either for fishing or for mills. These are being removed to allow the river to run more freely, but this has a measurable impact on the water temperature because you're shortening the residence time. Water is not being held in these pools and receiving the radiation from the sun, so it's affected the temperature of rivers downstream. So that's a good example of an artificial influence on the rivers. And then finally, does this have public resonance? Yes, it means that this information can be collected into documents and manuals for landowners to figure out when and where and how much tree planting they should undertake. So this indicator really has resonance with a landowning and river management community. So it ticks that box. It's a big tick for number 10 in terms of public resonance. So I hope you can see that how that, going through that process, how much was involved in developing this national indicator, which eventually appeared, I'm very happy to say, in this document that was put before our Parliament to show how our rivers have warmed in England since the 1970s. So these are some of the earlier data I was showing. So this indicator has been gathered together, put into this simple format, and then laid before the politicians, who then have to decide what are we to do with rising water temperatures? What can we do to manage this apparent increase in temperatures in southern England? So that's the sort of the very encouraging aspect of how a simple indicator that has public and decision-making resonance can really go a long way from science to decision makers. So in summary, I think for our national water temperature indicator in the UK, I would only give it 7 out of 10 in terms of the criteria that we've talked about previously. But I think there are some genuine concerns about the reliability. It's very sad to say that the networks are under threat all the time. Even the longest records are under threat. So probably fails on this front. And we have to always be mindful of these artificial influences on the indicator. And this is probably a factor that comes into play in most climate risk indicators. It's hard to find a pure indicator that is totally unaffected by humans in some way or another. Okay, so that helps you, I hope, see how we can think about risk indicators. We now come to the final part of the session today, which is an exercise for you to apply this thinking to some of the climate risks identified by USAID for Serbia. Now, this is a document that was published in 2017. I was looking at it this morning. Some of the commentary is already out of date, but I think it's a really useful, concise summary of the key impact areas of climate change on human health, energy, agriculture, ecosystems, and water resources. And what I'd like you to do is to spend, let's say, 15 minutes looking at that document and selecting one of the risk areas. And those of you who are in the room should have this handout where you can see the 10 10 facets of the climate risk indicator. What I'd like you to do is to identify one of those risks and start to devise your own climate risk indicator for something that is relevant to Serbia, if you're from Serbia. If you're joining us from another country, perhaps the Netherlands, maybe you can think about a particular set of indicator or an indicator that's relevant to the Netherlands or indeed in Norway. Does that make sense? So start by just browsing this document. It's very, very short, and then think about what might be filled into these 10 boxes in terms of the attributes of the climate risk indicator of your choice. What we're going to try and do is, at the end, pull together your ideas and see, you know, is there a 10 out of 10 indicator for climate risk in Serbia out there? What might it be? Or are we looking at 5 out of 10, 6 out of 10 for an indicator that's relevant to one of these impact areas? Does that make sense? It also, through this exercise, it helps us to also identify as scientists what actions might be taken by agencies or authorities to improve the information needed, or to protect the information or improve access to information to support the development of national climate risk indicators. Okay. Does anyone have a question online before we spend 15 minutes on this task?
Yes, I have a question.
We've got a question in the room. Yes.
It's about that graph you showed about temperature shock wave.
Yeah.
So can you please put that slide on so I can explain what my question is
Okay.
about?
So we'll go back to the start of the story, wasn't it? That one.
Okay, so when we look at the vertical line,
Yeah.
that is somewhere like
Downstream.
down. Okay,
Yeah.
but here we have two peaks, shock waves, if you agree. So
Yeah.
does it mean these are two different rainfall episodes that occurred only in that part?
Yeah. Great question. So the question for those of you who might not heard it at home is, how do we account for the two peaks in the purple curve? Now, what we have to remember is that as you go downstream, you're going to have the chance of flows coming in from tributaries the further you go downstream. So the interpretation becomes more complicated, because you could have a shock wave coming from one tributary joining a shock wave from the main stem, and they may not be synchronized in time. Okay, so this might be, you know, if this is the response of the water temperature, the shock wave as it's moving down the main part of the river. This might be another shock wave that's coming from a tributary that has joined the main stem of the river at a later time. So it becomes hard to interpret the further you go downstream, because you can have influences from tributaries and different sources. Whereas closer to the headwater at the top, it's simpler to interpret. Okay, does that make sense?
Yes, I didn't think about tributaries.
Yeah. But it's similar, actually, you know, when we're analysing flood peaks, which might have a complicated form, because we see the flood peak moving downstream, but also changing in its shape as it goes downstream because of tributary or structures in the river that delay that peak. Okay?
Okay.
All right, so let's say we will come back together at 25 minutes past the hour, okay, to share our thoughts in terms of the climate risk indicator, its purpose, and how well we can address those 10 criteria. Have we got any questions online, Jana?
No, nothing.
All good. Okay, so let's see what you can come up with. Develop your own climate risk indicator. Thank you. All right. Okay. All right then. Welcome back, everybody. Let's just, for way of reminder, go to the list of the 10 criteria that we're seeking to meet. So, anyone within the room, do you think you found a 10 out of 10 indicator? No, everyone's got a 10 out of 10 indicator.
Or just the one that falls every indicator in Serbia open data.
Okay.
That's the one that's
Yeah.
working for each indicator.
Okay, so are you recording this as well?
Yes.
Okay. So, no 10 out of 10 indicator. Well, I'm actually kind of pleased to hear that, because that's one of the key messages from today, is that there is no such thing as a perfect climate change indicator. It's virtually impossible to address all of these criteria simultaneously. And these are just my personal reflections on the criteria. Someone else might say, you know what, you're missing something, or you should you take away or add something. So it's impossible virtually to find a perfect climate indicator that meets all of these criteria. So whenever we're developing a climate change indicator, we have to have a big dose of pragmatism. Just got to be practical about what's the most important thing we want. It may be that we're looking for an indicator that takes the message to the public. And maybe if we go back to that opening one on dengue fever, if dengue really is something to be worried about in Serbia, then maybe we need to develop a dengue fever indicator that, above all, has public resonance and is communicated in forms that will help the public understand the risk and the need to take action, as well as for those in authority, the steps they need to take. So these have to be developed with a very sort of practical, pragmatic point of view. Okay, so no one got 10 out of 10. Did anyone get 9 out of 10?
We think we got.
We think we've got someone in the room with 9 out of 10. So, Minusha, perhaps you'd like to come up here and just walk us through your indicators. You're on the camera now, so you're performing.
Yes. Okay, hello everyone. We worked together in a team with my colleague Douglas Sapavic, and we thought of this indicator that is the data on daily water levels in rivers. So that is the data that goes back 120 years, and we scored it, and we think that we have a 9 out of 10. So water level in rivers. So the first point is benchmark. It is benchmarked. We have multiple stations on the river where we measure the water levels in river.
And perhaps if I can just interrupt you at this point. So here there was a little bit of confusion about the definition of the term benchmarking. So perhaps an easier way to understand this is a reference point. So something against which we can compare either in space or time. So think of benchmarking as the reference point. Okay.
Sure. So we can identify different influences on different points along the river.
Great.
Because we have multiple places where the river levels are measured and recorded. So is it sensitive to climate? It is with, of course, a little caveat of human anthropogenic influence. So the amount of precipitation, of course, will influence the water levels, maybe with some delay. So not instantly, but we can observe the falling of water levels in rivers according after the dry periods. So I think that is
That ticks
sensitivity.
So you're doing well. We've got 1 and 2 both ticks.
Yes.
Is it
If everybody agrees?
Oh, yeah, no, it's always challenging you.
Yes. So is it relevant to decisions? It is very much, because it affects energy production, hydro energy production, transport. It affects water supplies. So we saw this actually this year that when had many problems with water transport and so on, and very low levels, historically low levels in our rivers. So
Tick number 3.
not yet. Is it based on long series? It is, because we have records going back 140 years, so the end of the 19th century. So this is okay.
But not all.
Yes, not all rivers, of course, for a limited number of stations, but we do have some. Yes, excellent. Is it based on open data? These data can be found in yearbooks of the hydrometeorological service. So in a way, it is accessible and
Only for a small number.
for a small number. Yeah, yeah.
It's not.
Maybe
With,
Ninja, we should give
yes.
you just half a point.
yes,
for that.
I agree. I have to agree with that. Yes, that's true.
Very good.
Yes. Is it based on reliable data? Well, this is also up to discussion, but these records were made by the official hydrometeorological services.
And presumably they have quality assurance regimes in place.
Yes, so we know the methodology, we know the places where these measurements were made, so we can maybe factor in that changes that have been perhaps
Very good.
happened. And are they readily updated? Yes, they are recorded continuously. Are they affordable to maintain? Well, it is affordable to measure water levels in rivers, so it is. And for these confounding factors, of course, the answer is no, because we had major river regulation changes and building of dams, riverbank changes. So the human factor is indeed has changed that actually the process. So the discharge and the river water level regime is changed by.
And that's one reason why often a river flow risk indicator is taken from a headwater where you hope to be above
Yes.
most of the influences.
Yes,
Yeah.
yes, yes.
Okay.
And-
So you lose a point there.
Yes,
on that one.
yes. And public resonance, of course, this is a very visible and problem that can be felt very intensely by the public, can be understood good by the public. So this is, I think,
Excellent. Okay, thank you very much.
Thank you.
Nietzsche. I think that's a strong 8.5 out of 10 for water level as a climate risk indicator. And I think, water levels do indeed figure prominently amongst the risk indicators of most national risk indicator sets. So I think that endorses what you've just presented. So we've got an 8.5. Have we got anyone else in the room or online who would like to turn on their mic and share their ideas?
I was thinking something similar to them, but not quite the same.
Okay, what's your indicator?
Well, actually, my indicator is about percentage of imported energy. It's because Serbia makes its energy on hydropower.
Okay,
So when our water levels are low, we need to import.
okay. So for the benefit of those remotely who might not have picked up the sound very well there, we're talking here about for the energy sector, looking at the amount of imported energy coming into Serbia as a climate risk indicator. So out of the 10, which do you think does that indicator not address? Which of the 10 are problematic? So for water levels, it was problematic for open access and confounding factors. What about water energy imports?
Well, I think that a lot of things can also affect the energy imports, not only the climate.
Yeah.
But I think that this is something, these numbers are tracked on maybe daily basis. Because it's very important, because the country relies on energy usage. But also we had wars in the 19th, so I don't know how is there a database covering these war times.
Yes.
So reliable.
So the reliability issue and the homogeneity of the data, because there may have been times in the country's history when it wasn't possible to capture the information in the ways that we might do today. Okay, very good. Anything else on your list that might not be complying with the criteria?
Well, I'm not sure about this public resonance, because these data are only available to a small amount of people, which makes decisions. So we are probably right about the amount of
It's not public. Not public.
Okay, so it's not publicly available. It might be hard to communicate and explain what the information, not only what is the information telling us, but why does it matter? So maybe for your indicator, we're probably looking at about 6.5, 6.5 out of 10. So, but there are some sort of common messages already beginning to emerge, that the no confounding factors is a really hard one to achieve. In reality, we can try and do that by selecting what we would say in English is a sentinel site. I don't know how that translates. A sentinel site, so a location that just gives you a really early warning and is immune from artificial influences. So these are often in headwaters, if we're talking about river systems, or out in semi-natural landscapes and environments where the human influence is less. But the no confounding factors is a hard one to address. The other solution is to capture information on the confounding factors. So if we're looking at water levels, what are the amount of reservoirs, upstream water abstractions, so you can correct the data for those artificial influences as a solution. But then that in itself brings in further uncertainties in terms of the methods you apply. Okay, so we've had an 8.5, a 6.5.
We have also 8.5.
Would you like to come and explain which one did you, or yes, come on camera.
So I think we were choosing the precipitation data because we wanted to address risk declining in agricultural production.
Okay.
So first the benchmark. We have here spatial temporal coverage of Pannonian Basin for 2 climatological cycles. Okay. So it's okay. Then sensitive to climate, the precipitation is very sensitive. The precipitation data is very sensitive to climate. Right. When we are discussing relevancy, it's very relevant. Based on long series, yes. So here we can address more databases. We chose ECAD because ECAD has station data. Okay. And if we are talking about open data, ECAD is also an open database. But when choosing open database, here we have a question: should we use station data or grid data sets? Okay. Or maybe both. Or maybe some reanalysis.
Or reanalysis or radar data. So I think whether you use station data, gridded data, reanalysis, or radar data, or remotely sense, rainfall measurements. They all have their strengths and weaknesses.
Yeah.
And the station data set is likely to be longer, isn't it? So all
Yes.
brown, so that might give a better indication of the long-term change than say a radar data set, which would probably be much
Yeah.
shorter.
Well, exactly. Point 4, 5, and 6. Either the data sets you're choosing, you're messing one
Yeah.
number
Yeah.
down.
Okay.
So I think it is, from my point of view, impossible to reach 10. But okay, let's go further. Is it reliable? Well, data quality inspection should be always in here stated, and station data are better due to calculation trends.
Yeah. Okay.
And is it readily updated? Yes, but carefully selecting the station,
Good.
the station
Yeah.
selection. Affordable to maintain. Okay, yes, because it is open data set and it's free. No confounding factors. Okay, here we have a mixed answer here, and reliable data is where we are losing
Okay.
the half point.
Yeah, because the location of the monitoring site can determine the quality of the
Yes.
rainfall.
Yes, and I was thinking that you must be very careful in reading the peer literature, what the other peer researchers have discovered when they were doing their research with the open databases.
Okay.
And the public presence, okay, this is very important because Pannonian Basin is the agricultural area, so it has the stakeholders interested in this subject.
Excellent. So you think you get an 8.5 out of 10? Okay, very good. Thank you very much. All right. So thank you for everyone who's joined into this task. And
We have a comment.
we have a comment. Okay.
From my specification network. Plotting damage transportation network increases risks like road accident and can cause transportation delays infrastructure damage, supply chains food, and therefore can cause damages in economics.
Okay, great. So as a transport-based indicator,
Yeah. So probably due to the, so yeah.
yeah, that's very good. In fact, in the UK, we've got quite a bit of research going on at the moment into climate links to transport infrastructure, including, for example, the impact of floods on emergency responder times as an indicator of climate risk. If it takes someone longer to reach you in an emergency, in a flood, in a fire, if you're unwell because of flooded networks, then that's obviously a significant thing. So thank you for that comment.
We have another comment.
Yeah.
Increased illnesses and mortality for kids serve only 4 out of 10.
Okay.
And I just asked, could you please specify which 4?
Okay.
So,
Okay. That's a really great indicator to have. You know, that hospital admissions,
Yeah.
hospital data related to heat waves and associated health impacts requires very careful categorization of why the person's coming into hospital, and so those data aren't necessarily publicly available.
in Serbia, not publicly available. Try to find some data about heat waves and during the heat waves, but even in the hospital, they don't characterize, for example, the symptoms to, they don't link the symptoms to the high temperatures.
Yeah, that's good. Yeah, so who was that who contributed that one?
I think that I'm not very sure that there are only initials.
Oh, okay.
So,
Is that VM?
yeah, yes.
VM, thank you for contributing that. We'd like to know if you could quickly type down which are the 4 out of 10 that you think got right.
I just wrote, can specify which 4, but
Okay.
no answer.
All right. I'm guessing it would score well on public resonance, so being able to alert the public in terms of the risk of heat.
Long series, maybe that's what's missing, because in the hospitals, if they keep track, there will be maybe 10 years of data or so.
but it probably scores on sensitive to climate
And relative to decisions.
and relevant to decisions.
And maybe benchmark, it is really important to have that.
Yeah, we know physiologically
Yeah.
what temperatures and humidity cause certain symptoms or impact people's ability to work or function. So those things are known. So thank you very much.
The answer is that sensitive to climate,
Thank you.
relevant to decision,
Yeah,
based on reliable data, there are some, and public resonance.
excellent. Thank you very much, BM. That's a really good one to contribute. But here we go then, just to sum up, I hope through that little exercise, you can see how we can start to think about the development of the climate risk indicator in a more structured, systematic way, recognizing we're unlikely to achieve all the criteria that we want. Often we find the confounding factors is a common obstacle, but there are some solutions to that. And just from the examples we've gathered in the room and from those joining us remotely, we can see the diversity of sectors that can be covered. We've got health, we've got transport, we've got natural resources, water, and we've got flood risk and agriculture covered by what we talked about today. So thank you very much for your engagement in that. Just a few concluding remarks. So I hope from the exercise and from the talk this morning, you're able to see that indicators are a powerful tool. They can also be the entry point for all sorts of really interesting and exciting research that could be undertaken from undergraduate level through to PhDs and postdoctoral researchers. I hope you can see that we can develop indicators for our own universities, our own cities, and right up to national scale indicators with the available data. Why are we trying to do this? Well, this basic idea that in order to manage a risk, we need to be monitoring that risk. So monitoring to manage. I'm always referring to running an athletics type analogy. So it's kind of taking the pulse check, taking our pulse, checking that, you know, how well are we performing. We need ideally to be developing indicators that can track changes over decades, and that is often a limiting factor because of data availability. But increasingly, we're seeing around the world big efforts, whether through research grants or through citizen science initiatives, where people are digitizing old data sets to put them to rescue data and restore and lengthen existing data sets. Indicators can help us evaluate whether or not the actions that we took as a society had a benefit. So going back to that really nice example of heat impacts, if you've got a long enough record, you might be able to see to what extent a national heat warning service or alert system reduces the number of people that are being made unwell because they're being given advance warning to take action and advice on what to do. So these indicators can help us to understand the effectiveness of our climate actions. And whether it's in a map of dengue fever spread, whether it's in a time series of flood risk, whether it's in a forecast or a piece of advice on health actions, is a very powerful mechanism for communicating for diverse audiences, whether it's the public, a hospital administrator, a government agency, or the research community, and you can reach lots of audiences. When we look at what is being done globally in terms of climate change risk indicators, there are some recurrent gaps. So often there's very little, if any, information on changing societal behaviours and attitudes to those climate risks. So information about people is often lacking. So what changes in behaviour do people adopt during a drought in terms of their water usage? For example, we have relatively little information on the actions being taken to adapt to climate change. So finding really good data, for example, the number of homes being upgraded or retrofitted to protect against flash flooding or whatever. These data are hard to obtain as well. Then there are these bigger risks of climate change to systems of systems, recognizing that a flood not only has direct impacts on people and property, but can have indirect effects on IT systems, transport networks. So, and here I mentioned the emergency response times that are affected by floods. So understanding not just the local, but the system of system impacts of climate change. There's not much data on that. And finally, the pandemic has taught us internationally how vulnerable supply chains can be to all sorts of factors, including climate disruption. And this is an area again where the vulnerability will depend very much on the national circumstances. So, for example, in the UK, we're increasingly dependent upon imported food. So the food security and the price of food is linked to these international supply chains, which are potentially disrupted by droughts and floods and other factors around the world. So understanding that those national linkages is important too. Those of you who'd like to explore this topic in a little more depth, I've suggested a couple of readings. These are on the OneDrive, I think. Yeah, they've been uploaded there in the public domain. So Nigel Arnell and others have developed a set of climate risk indicators for the UK to show how different sectors might be impacted by different amounts of global warming. So, and this is again a very powerful way of linking global change to national and local impacts. So we're able to say, this is the consequence for water resources or agriculture if there's 1, 2, or 4 degrees of global mean warming. Okay, so benchmarking the impacts, the risks of global mean temperature is increasingly being used by policymakers to show what the benefits might be of, for example, cutting the temperature, containing the temperature from 2 to 1 degrees of warming. Okay, and then finally we've got a paper here which goes into much more detail, talking about how we really need to understand some of the intricacies and uncertainties in the index and how it might change under climate change. And this is done with respect to a range of hydroclimatic indicators. So how do we calculate the indicators? What's the reliability of the data? How might the sensitivity of that indicator change under different types of climate scenarios? So that's really for the specialists here, if you want to take a super deep dive into the subject. So finally, before we close, I just open up to whether there's any remaining questions out there. Anyone has a question or something I've covered that wasn't clear? Any comment on what we've covered today?
I have a comment.
Yeah, okay.
First, about this climate risk profile that you gave us, this document.
Yeah.
Here we have a map of Serbia with different climate classification.
Yeah.
And here we can see also polar and tundra
Yes,
climates
yeah,
in Serbia. I think that it's not true. I want comments from my professors. So here near the border of Macedonia and Bulgaria, they presented that we have a polar climate.
Classification. So when you go to see the different classification of the world, you can see the exact class
yeah,
description.
Yeah.
So then you figure out it's not just like polar and
Yeah.
kind of like in
This is the one that
yeah.
you can get into
Yeah.
classification. So this is highlands.
yeah. So for those of you joining us remotely, the question is, what's behind the climate classification in Serbia climate risk profile? How is it possible to have a tundra climate? Well, that tundra is probably a generic term which is being used to describe high altitude environments that are have a certain temperature and rainfall and snowfall regime, certain parts of the amount of time where the soils are frozen, that kind of thing.
So it's
So-
only cold.
Sorry?
So it's only cold, like polar and tundra. It's
Yeah,
not-
yeah, it's not saying it is tundra and polar,
Yeah.
but it's a descriptor. And those climate classifications are, quite often used in these high level assessments to allow some commonality between the studies.
Yes, I agree with you, but I need to point out that in this part of Serbia, there are not that high mountains. We have higher
Yeah.
mountains in some other areas.
Yeah,
Here, especially with the borders,
Yeah.
the northern part of the border with
Yeah.
also with higher mountains.
yeah,
And even with our like the easternmost part of the country, there are high mountains. So I was not sure.
no, I think what you've touched on is an important point, which is in these kinds of high-level national assessments, and there are many examples of these types of high-level summaries, often are undertaken remotely or as a desk-based analysis, and maybe not involving researchers or people from Serbia who can ground truth the information. You do quite often find things that are puzzling. So I, for example, I won't name the country, but I've seen one climate risk profile for an entirely landlocked country where it still had a category for sea level rise. So, that's an example where someone's applying a generic template and didn't say, well, this is a landlocked country. There's no point saying low risk to sea level rise because there is nil risk of sea level rise. Okay,
But it's also maybe the resolution, temporal and
Yeah.
spatial resolution of data used for the building this map and calculating the
yeah,
climate classification can also be the source of
Yeah.
problem.
yeah. Data issue, spatial resolution, lack of local knowledge, ground truthing. These can all be factors. So I'm really glad you mentioned this because these, national risk profiles are often simplifying things to a level where you can begin to challenge some of the content. That said, I think that the tables that I asked you to look at under the 5 impact areas do give you a starting point to think, okay, if we're concerned about heat, if we're concerned about agriculture, what type of index might we be able to develop for Serbia to reflect the national circumstances? So it does, think something like this provides a starting point to get the discussion going. But that's it. Okay, thank you. Any other questions? Anyone online? Okay, if there's no other questions, do you want to close
Yes.
proceedings? And thank you everyone for really engaging with this these exercises today, home and abroad.
Yes.
It's always difficult when we're in dispersed mode, but I hope the structured approach that I've laid out here helps you think about how you might go and develop your own climate change indicators.
And how can we influence others like decision makers in the government to take a closer look into science than just, saying what they heard from global, global in global meetings or in some regional meetings.